All right. So, before we get going again, there we go. I think that I misspoke on Monday on this slide. So I want to clear that up. So really, it has to do with the temperature and the heat exchange that goes on here in the absorption process. So absorption and adsorption are both exothermic processes. So when a substance gets absorbed or adsorbed, it releases heat because you're going to a lower energy state. And so the what goes on here is that you have this heat exchanger, but really in the stripper column, when you remove that, you have to heat it up again because desorption is an endothermic process, so it requires heat to function. So I just want to be clear about that this step here releases heat, and this step here requires heat. So that's what's going on here. And this is important for what we're going to talk about today, which is how adsorption and desorption work in the context of physisorbents and chemisorbents. So let me go through here. All right. So we were talking about adsorption on Monday when we finished up. And just to remember, adsorption is when all the action happens right on the surface of a substance. So you can think of this as the CO2 molecules out here do something at the surface here. They can either physisorb or they can chemisorb. So in this case, you're looking at van der Waals interactions that cause the molecules to preferentially stick on that surface. And for chemisorption, that's going to be chemical interactions, chemical bonding, actually. But again, it's happening right there on the surface, as opposed to actually going in to this blue phase and interacting with the molecules that are in there. Okay, and so we talked about the different types of physisorbents. A lot of them are either zeolites or activated carbons. These are very good. They typically have very large surface area, and they're very good for a lot of uptake of chemicals on their surfaces. Activated carbon is used in a lot of purification processes because it's not just CO2 that will interact with the surface, but a lot of different molecules can preferentially adsorb on some or all of these different functional groups here. So activated carbon is a really good thing. But I mentioned that probably the most advances we're going to see in sorbents for direct air capture specifically are these metal organic frameworks, which are really cool molecules that can be engineered to give you preferential sorption behavior of certain molecules. Because this is a really big problem with these sorbents, is that you get these competitive effects. And so if you've got carbon dioxide, nitrogen, and water vapor, for instance, which might be the typical composition of a flue gas stream, you want that sorbent to only take up the CO2. Or another thing is if you're looking at the ambient air, there's so many other things in the air, nitrogen, oxygen, argon, that again, you want to just be targeting the CO2. And so this allows you to really fine tune the molecular structure of these metal organic frameworks. You can also give them a very high surface area because they've got this microporous structure. So this is where a lot of work is focusing right now. The drawback with MOFs is they're expensive. And so, and I think part of that has to do with right now, there's not the economy of scale that you would get, say, with making activated carbon. These are still a little bit of a boutique chemical. And so, as that production gets scaled up, you probably will see the costs come down. But that's a significant barrier right now to their adoption. Okay, so that's the type of sorbents. Now, how do these things actually work? There's two different ways that these sorbents can be used. Basically, you need a way of getting the CO2 in there and onto the sorbent, and then removing it from the sorbent when all of the sorption capacity is used. So there's two main types of reactors that are used for this. There's a fixed bed and a fluidized bed. The fixed bed is pretty easy to imagine. You've got, the incoming gas stream here. It could either be flue gas, or if you're doing direct air capture, it can just be ambient air being blown in there. And you've got some arrangement of the sorbent in here. A lot of the time they're arranged in layered kind of trays that are in here. I think when we had our group presentations last week, I think at least one group showed the setup that that company Heirloom has out in California. They have a huge stack of these, sorption beds. So the more of them you can stack up, the higher your sorption capacity is. But basically, your feed stream comes in the bottom, and then what comes out of the top hopefully has been depleted of all of its carbon dioxide. Eventually, the sorbent that's inside here reaches some maximum sorption capacity where you've occupied all of the surface sites that are available for sorption. And then at that point, you need to desorb the CO2. And so you'll flip the airflow around. You'll put a purge gas through here. And we'll talk about how that works in a minute. But that will cause all the CO2 to desorb, and then you'll capture the CO2 out the other side. So it's a pretty simple setup. The downside is that you periodically have to shut the whole thing down and purge it to keep operating. And so to get around that, there's another type of bed called a fluidized bed, which is a little more complicated, but it can operate continuously. And so it's got two sections, one on top of the other. The flue gas comes in here, and it migrates up through these trays of sorbent. And that's pretty much the same way that the fixed bed reactor works. But the other thing that happens is that you have a flow of the sorbent back down here. So that's why it's called fluidized. The sorbent isn't just sitting there. And so it takes up the CO2, and they fall down into the bottom here where you have your desorption section. And once the CO2 has been desorbed, they're pumped back up here through with a carrier gas back up to the top. And so this allows you to have a continuous operation, and you don't need to shut it down to purge. The problem is that there's obviously a lot more moving parts and stuff in these fluidized beds. More things can go wrong, components can break. So you have to figure out what trade-off you want to make with fixed versus fluidized beds. Okay, so that's the basic working. Now let's get into a little bit at the molecular scale of how adsorption and desorption work and how these different reactors function. So the simplest way of understanding the adsorption and desorption process is if you think of the surface of your sorbent as just a flat surface with a whole bunch of sites on them where the adsorption can happen. So in the case of chemisorption, this is pretty easy to imagine. These would be active sites where you can have chemical bonding happen. In the case of a physisorbent, like a zeolite, you could think of these as those, potential wells where you have the favorable van der Waals interactions that cause the CO2 to stick there. But anyway, so we'll mark those with an X, okay? Now, if you put this sorbent in contact with the gas that you're trying to adsorb, we call that the adsorbate. Some fraction of those adsorbate molecules will go to the surface, okay? Not necessarily all of them, but some fraction. And so the assumption here is that you can have one molecule on each sorption site, and the adsorbed molecules have absolutely no interaction with each other. They just go to the surface and they stay there. They don't care about who's around them, right? So that's our basic assumption. Now, if we think about the kinetics of this process, there's always going to be some exchange back and forth between the adsorbent surface and the gas phase. And so we'll assume that there is some flux between the gas phase and the surface. So We'll call the desorbing flux, we'll call that K desorption. And we'll assume that that's going to be somehow proportional to the number of molecules that are actually on the surface, which makes sense. So if you have more molecules there, more of them at any given time may be leaving that surface, okay? And so we'll call theta, did I define that already? Yeah, so theta is the fraction of the surface sites that are occupied. N max is going to be the maximum number of the total number of surface sites, okay? So theta times N max is going to be the occupied number of surface sites. And then we'll have some constant of proportionality here that we'll leave undefined. Okay, so that gives us the flux leaving the surface. We'll assume there's also a flux of molecules going from the gas phase down to the surface. And we'll again assume that that flux is proportional to the number of molecules that are in the gas phase. And so we'll represent that with the pressure of the gas phase. And so here we have 1 minus theta. So that's the unoccupied fraction of the surface sites. And then the pressure is a stand-in for the number of molecules. And then we have another constant of proportionality just thrown in there, so we can have an equal sign. Okay, so those are our two fluxes. We have some molecules that are always going to the surface. Some of the molecules on the surface are always desorbing. And so if we're at equilibrium, those two fluxes have to be equal. So we set them equal to each other. And then we can solve for theta. And what this gives us is the fraction of the total surface sites that are occupied as a function of pressure. So everything cancels out here. And we can represent the two constants of proportionality with a single constant, which we call B. And what we see is that at a given pressure, the fraction of surface sites is given by this equation. Now, this equation is called an isotherm because it assumes that the temperature is constant. So as we vary pressure with a constant temperature, we can calculate what the fraction of occupied surface sites is going to be. And this particular model, this is called the Langer isotherm. And the Langer isotherm, again, is derived using the steps we just went through, where you assume that the molecules on the surface form a monolayer. There's no stacking of molecules on top of each other, and they don't interact with each other. And so it looks something like this. So as you increase the pressure, more and more of the possible surface sites will be occupied. It never gets to theta equals 1. I mean, I guess it would get there at infinite pressure. But there's a theoretical maximum. And so this allows us to figure out as a function of pressure how the sorption varies. Okay, so in practice, what this means is that the easiest way to get CO2 molecules to desorb from the surface is to reduce the pressure. Okay, and so that's one way of doing it. So you can design your reactor such that it operates at some elevated pressure, and then when you're ready to do the desorption step, you just pull the pressure down to atmospheric, and the CO2, all or some of the CO2 will come off. Okay, there are other ways of doing this also, where we can talk about how the temperature can cause this to vary as well. And so to do this, let's assume we're operating at more or less ambient pressure. And so what that means is that we can express the isotherm simply as B times P. So now it's just linear in pressure. And we can re-express this in the terms of the number of adsorbed molecules by remembering that theta is just the number of molecules on the surface divided by the total number of surface sites. And we get this equation here, and then we replace these two terms out here with Henry's law constant, which is all that ends up being. Now, this allows us to use what's called the Van't Hoff equation, which tells us how the Henry coefficient varies as a function of temperature. And we see this right here. It's given in terms of the heat of adsorption. So now we can see how the amount of CO2 on the surface will vary with temperature as well. So if we integrate that, we see that the change in the natural log of the Henry's constant is given in terms of two endpoint temperatures. So you can look at that change as a function of changing the temperature. So what's interesting here is that if we're increasing the temperature such that T2 is larger than T1, what that means is that the Henry's constant actually decreases with increasing temperature. So if you go to a higher temperature, you actually end up reducing the sorption capacity of your sorbent, which is kind of counterintuitive. But if you think about it in terms of the kinetics of the gas, the gas is going to have more energy and it's going to be less likely to go to the surface if the molecules are all moving around in a more energetic fashion. So this is just something you have to think about. So increasing pressure causes more sorption, but increasing temperature causes less sorption. So we can use those two facts to design our sorption and desorption steps. And so typically what we do is you'll have a either a pressure, what we call pressure swing, or a temperature swing desorption, or some combination of those two. So in a temperature swing, what we do is we actually purge the reactor with heated gas, because that is going to reduce the sorption capacity. And so in your so you start off with just absorbing at ambient conditions, and then you purge that with a hot sweet gas. And so, you're never going to completely desorb all the CO2. There's some what we call working capacity, which depends on the temperature difference that you're imposing. You can combine this with a pressure swing also to get more to desorb. The pressure swing is a little bit easier to understand. So you'll be operating at whatever your operating conditions are, and then you'll just reduce the pressure and let the CO2 come out. And so you can figure out your temperature, or your working capacity as a function of the pressure swing also. Now, obviously, like we talked about before, these desorption processes require some kind of an energy input. You're either pressurizing and depressurizing the system, or you're purging it with heated gas. So you've got to have ways of having the energy input here to make that happen. But this is the simplest way of making it. Okay. So that's how carbon capture works. It's really just a matter of getting the CO2 in contact with something that either absorbs it or adsorbs it, and then purging those sorbent of the CO2 and then capturing. Okay. Any questions about carbon capture? No. Okay, fantastic. Let's move on to our next topic. Okay, so next up here is carbon utilization. So you probably can tell we're stepping through the CCUS. So we just did carbon capture. Now we have carbon utilization. And so the setup here is, let's imagine that you've captured some CO2. And so the question is, what are you going to do with it now? And you really have two choices. You can use it for something, right? Or you can simply dispose of it. So today we'll talk about the using it step, and then probably Friday and next week we'll talk about the disposal step. Okay, so the U.S. Department of Energy has a very nice carbon utilization program, and I pulled this slide from them. But there's really, they see 4 ways that you can utilize captured CO2 for different things. You can make fuels or other chemicals out of them, so that's the conversion step. There's what they call uptake, which is you can basically use algae to take that CO2 and convert it into more useful things. And then there's mineralization, which involves making various inorganic materials like, I remember hearing about some scheme where they were going to take captured CO2 and make baking soda with it. So that's an example of something you can do. But there's a lot of other things you can do under the mineralization side. And then you can actually use CO2 as a working fluid. And what I mean is as a working fluid, that's like in some type of a heat pump or a heat exchanger. The CO2 actually has some favorable qualities for use as a working fluid. We'll talk about that. Okay, but I'm going to start with algae. It looks kind of gross, but it actually it can be very useful. So there's a company called Qualitas, which has built this algae farm in New Mexico. And the way this works is they've just got these tanks that are filled with algae. And they're actually taking up CO2 from the air and converting it into other things. But you can also imagine, having a CO2 stream from some kind of a direct air capture system go in here and enhance the rate at which the algae works. So the basic way, it's very simple. Algae is a plant. And so they combine the CO2 and water with sunlight, and they go through photosynthesis. And what comes out is oxygen and then biomass. And the biomass is what's really useful here. So a couple of years ago, I supervised a senior design group out of mechanical engineering. And their project was actually building a small-scale direct air capture system where they had it hooked up to a tank with algae. And it was really cool. It worked out really well. They called it the carbon farmer because you were basically farming the algae in there. What's really nice about combining algae with direct air capture is that the algae doesn't need a highly pure stream of CO2. Okay, so if your capture efficiency is not very good, which I think in the carbon farmer, the incoming stream was at 420 parts per million, and I think they were getting 600 parts per million out. So it wasn't like ultra pure CO2. But the algae doesn't really care. In fact, that's better. There are certain strains of algae that can do well up in elevated concentrations of CO2, but not all of them can. And so that's what's nice about the algae uptake. It's very forgiving. Obviously, it requires water, it requires surface area. So, you're not going to cover the entire surface of the earth with algae, but it's a good thing. And so, like I said, the biomass is the useful thing that comes out of this. And let's see, yeah, I'll talk about the uses in a little bit. But the algae actually also has a lot of advantages over traditional biomass manufacturing, which, is a fancy term for farming. But, it requires fewer nutrients. It doesn't require a lot of, fertilizer or that sort of thing. You can harvest it frequently. The algae grows pretty rapidly. And, the nutrients that you use to grow the algae can be recycled much more than with conventional farming. So you have a lot of advantages to the algae. And the stuff you can do with it is you can use the biomass that it makes to make all kinds of things, including food additives. So if you think about these meat substitutes that a lot of them are being developed today, algae biomass can be potentially used as a protein substitute in those, Beyond burgers or whatever. But there's other things, livestock feed, fertilizers, but you can use them a lot for biofuels. So you can make bioethanol, jet fuel, things like that. And it's valuable, which is the main thing that we're going after here. So that's what's really nice about algae. Okay. I always enjoy standing here and lecturing and watching people get stuck at the gate. Like that bus just pulled up there, like, bro, what's your plan? All right. Okay. Now, the second thing is mineralization. And I think this is one that has a lot of potential in the future, because there's a lot of materials that you can make out of CO2 in a mineralized form that are very useful to what we do today. So that includes things like concrete, cement, various other building materials, and then a lot of things like, pigments for paint and things like that can also be made out of mineralized carbon dioxide. So, so a good example of this is upcycled concrete. So when I was putting this lecture together, I did a Google image search for upcycled concrete, and I found, you can make a cactus planting bed, or, you can hold your beverages in it. But that's actually not what we're talking about. Not that kind of upcycling. Although I'm curious if any of y'all would spend a night in this place. I don't know. It'd probably be keep you very cool, I guess, on a hot day. But what upcycled concrete refers to in this context is actually adding CO2 to the concrete. And this has a lot of advantages. So what they do is they add the CO2 here in an extra mineralization step after the concrete is made. And the CO2 gets in there, and it actually enhances the strength and the I think offers some corrosion resistance also to the concrete. So it's can be a potentially a good thing. And if you think about it, I think we'll talk about this later, but cement manufacturing is a huge emitter of carbon dioxide because of the chemical reactions that happen during the process. It's basically the limestone decomposition releases CO2. And so if you can actually, capture some of that CO2, or maybe capture some from a power plant or something like that, then you can sequester that into the concrete. And that has a number of advantages. Not only are you increasing the durability of the concrete, but you're reducing the carbon intensity of the cement manufacturing process. So I think this is pretty cool. I know of a company out of California that is, well, actually, no, this is what Heirloom is doing with the CO2 that they captured. They're using it to, to enhance the strength of concrete. And I just read the other day that, what's the, not Labarge, but what's the other big concrete manufacturer? And anyway, I forget who it is, but a cement company announced some partnership with a direct air capture company to do this. So I think you're going to be seeing more and more of this. Cement is kind of on my mind right now because they're building, the new EDB next door here. And, just the amount of concrete that's going into that building and the amount that's used in general in our built environment, it's really something. So, thinking about reducing the carbon intensity of building materials, I think is a good thing. All right. There's all kinds of other things that you can do with mineralization. So, Alcoa is using it to treat the waste that comes out of an ammonia plant, actually. So that's one thing you can do. There's this company called Carbocrete, which they're looking at using it to activate steel slag. So this is, basically making activated carbon. Here's another company that's looking at that. Let's see, nano carbonate crystals, carbonating olivine for making building materials. So there's a lot of cool stuff that I think we're going to be seeing in the near future. The technical readiness levels, I think I had a slide on that at some point, but basically TRL 6 to 7 is like proof of concept in the lab where you've gotten there, but it's not quite commercially ready. TRL of 9, that's kind of commercializable at this point, ready for market. So hopefully we'll see more of these technologies come along because I think, I'll talk about this later when we get to the end of Unit 2, but if you think about it, there's not really that much incentive right now for companies to be doing carbon capture and carbon removal except for tax incentives. And with maybe a little bit from carbon credits, but that's a whole other issue. But if you really want to incentivize companies to do carbon removal, it has to be a market for the CO2. And the easiest way to do that is to turn it into something useful. And hopefully we'll see more and more of these uses come along for this to work. And a really good example of that is carbon conversion. And what we see a lot of interest right now in what's called e-fuels. These are synthetic fuels that are made by combining carbon dioxide with hydrogen that's produced by electrolysis. And you really, utilize this syngas generation step to make those. What ends up happening is you can take the syngas, which is carbon monoxide and hydrogen, and you can combine them together to make various synthetic fuels, synthetic diesel, ammonia, methanol, things like that. And if you think about it, there's the potential that this could be a circular system that ends up being net carbon neutral, because if you burn the fuels, you emit CO2, but then you can capture that CO2 and use it to make synthetic fuels. And so in a perfect world, you're going to just be cycling around that cycle without any net CO2 emissions. Now, the problem with that is that the processes that you use to split apart these molecules and then recombine them, they require energy, okay? And so you have to think about where that energy has come from. If you're running an electrolyzer off of the grid, a lot of that electricity is going to come from burning natural gas, so et cetera, et cetera. So you have to think carefully about that. But there's a lot of interest in this that that I see when I'm talking to people out there in the industry. Okay. So one way of doing this where you don't require electricity input is photocatalysis. And I think, the interest in photocatalysis has kind of, risen and fallen over the years. I think, there's, certainly a lot of work going on right now on it. But the nice thing about photocatalysis is that it uses sunlight to provide the electrons necessary to split apart water, okay? And so, you take the CO2 and the water and you can split them apart to make so this is actually methanol that's being made in this photocatalyst, but you can design these catalysts to do, other things and make other molecules. And so just using sunlight. And so this might be a way of getting around the energy input, okay? There's a catch to this one, though, okay? There's no such thing as a free lunch. So this particular catalyst uses silver. Okay, where's that silver coming from? Well, it's mined. Okay, how are you mining that, et cetera, et cetera? Okay, so you get the point here. But, there's ways around that too. So I think this is kind of an interesting field of getting, that we can be getting into more in the future. Okay, and then the last utilization step here is as a working fluid. So working fluids are what are used in an engine or a heat pump, and you transfer heat to or from them during a thermodynamic cycle. So a really good example of this is a refrigerator. So the way the refrigerator works is you blow warm air across an evaporator coil, which has a working fluid in it. And what that does is it causes that fluid to evaporate, which takes up heat. And so you have cold air come out the other side. And then you run it through a compressor and through a condenser, which exchanges that heat back up. And so you run this whole cycle here. And so you can use carbon dioxide as your working fluid in here. Now, in a refrigerator, typically you're going to use a refrigerant like R834 or whatever. But you can use CO2 as a working fluid as well. And it's got advantages for this because it's got low viscosity, which means it's easier to pump. It's got a high compressibility. So when you run it through a compressor, you require less energy to reduce the volume. And it's got a low supercritical pressure. Supercritical fluid is basically a dense gas. It's got gas-like viscosity with liquid-like density. And you can get CO2 to a supercritical state pretty easily. And it's in its supercritical phase, it's twice as dense as steam, so it's got a higher heat carrying capacity. So, you know, there are a lot of advantages. I've seen actually people looking at using CO2 in closed loop geothermal systems as a means of you know, carbon utilization. So this is also a potential. As we'll see later on when we talk about heat pumps, I think it's in the geothermal unit. There are certain, you have to make sure you've got the right conditions where using this, you know, a particular working fluid makes sense. And, you know, to get to supercritical CO2, you're typically at like 70 degrees Celsius and 1100 PSI. So that's not going to be like in your refrigerator, okay? But there might be another situation where that does make more sense to use, like geothermal. Okay. Well, we got to the end of that in a hurry. I guess I had too much coffee this morning. I think rather than forging ahead into the carbon storage unit, we'll leave that for Friday. So you get 9 minutes of your Wednesday back. I hope you use it wisely, and I'll see you all on Friday.